Okay, part two. Group, this is just going to be a quick recap of what the part one video covered. This is trigonometric ratios of obtuse angles. So we're trying to determine the sine, cosine, and tangent ratios for angles that exceed 90 degrees. We're set up a new system, a new way of defining the ratio. Instead of using opposite, adjacent, and hypotenuse, we've now moved to definitions that use the coordinates of a point and the length of the terminal arm. So we have terminal arm, initial arm, and the angle formed is a standard position angle. That was defined. All right, and moving forward with those definitions for the labels for the sides of a right triangle, we have now coordinate definitions extending our opposite hypotenuse to y over r for sine ratio, extending the adjacent over hypotenuse to now rely on the ratio of x to r for cosine, and for tangent extending the opposite over adjacent ratio to use the ratio of the y coordinate to the x coordinate. We also need to know how to calculate the length of the terminal side or terminal arm. That's not information that we find directly from the coordinates, because those just give us the horizontal distance away from the origin and the vertical distance above the origin. However, if we need to use a ratio that involves the terminal side, which are the sine and cosine ratios, then solving for r is just one step past taking the x and y coordinates and applying Pythagorean theorem to get the length of r as the square root of x squared plus y squared. And that's how we've solved right triangles before, and you knew that that was a skill that you'd be using in this course, and here you find another application for it. So that's the length of the terminal. All right, and now for looking at what happens when our angle is in fact obtuse, greater than 90 degrees. Well, our terminal arm will now be located in quadrant 2, and we have to pay attention to the sign of our coordinates. So our point xy now will have a negative x value, a positive y value, which produces certain properties for the trig ratios that are going to use x and y, and all three will use at least one of those ratios. But good news is that we can calculate the ratios as we did before. Sine A is still going to be y divided by r, cos of A is still going to be x divided by r, and the tangent of A is still going to be the ratio of y to x, which I have compared to the slope, as it's quite similar to change in y over change in x. Okay, so I'm returning to the last or second last page of your handout package. The question number 3, which is found on page 23 of your text asks the question: what would be the trigonometric ratio for a given point on a coordinate grid, assuming that it makes a right triangle with the origin and the x-axis? So I've selected 3 parts of that question, one for sine, one for cosine, one for tangent. I'm going to draw this to make it nice and visual for us, and we're going to calculate what the ratio would be. All right, so the first one in number 3a is calculating the sine A for a point -4, 3. So don't try to avoid diagrams in this type of trigonometry. You need to make your solutions visual, and because this is a point on a coordinate grid, I expect to see a solution with a point drawn on a coordinate grid. If you want to just draw a y and x axes on a piece of lined paper, that's fine, but you need to show where your point is located and draw your angle in standard position. So we're going to go to -4 up to 3. You notice this is, has us in quadrant 2. Okay, and here's our angle, which we know is an obtuse angle. So we can, from there, draw our triangle, label our sides. That's going to be -4 along the x-axis. This is going to be 3. Our point we label up here, and then we apply our coordinate definition. Sine is, again, y divided by r. So the only thing we don't know yet is the length of r. It's not given directly from the coordinates, but we can solve for it as the square root of x squared plus y squared. And again, here, square root of -4 squared plus 3 squared, just show that extra step. Now, we should be able to calculate these mentally. Use a calculator if you need to. 16 and 9 is 25. The square root of 25 is 5. So the terminal arm is going to be 5 units long. Take our y-coordinate, which is 3. Our terminal arm length is 5. This trig ratio will be 3/5, which is, as a decimal, 0.6. So whatever that angle is, we don't actually know the angle, but we do know it has a sine ratio of 0.6. If we wanted to know the angle, at this point, you should be able to solve that. Angle A would be inverse sine of 0.6. The question didn't ask for the angle, it asked for the ratio. So your answer would be done here, 0.6. 3b, looking at the cosine ratio. 0.14 would be located in quadrant 1. Fairly steep angle. Draw your terminal side, drop down to the x-axis. Label your point, which is letter Q, 1, 4. Label the sides as we know them. X value is 1. We're 1 unit over from the origin at 0, 0. The origin is often labeled A in these examples, and you see in your text, and in the investigate, it was A, 1 unit over, 4 units up. Again, here for cosine, before you go ahead and solve for information that's not necessary, write the definition of this ratio. It's adjacent side that we always use for cosine. Nothing much has changed here, except now we're calling it the x-coordinate of that point. So, do we need r? Yes, we do. All right, well, that was just a bit of a test. We'll see for tangent, that won't be necessary. R here is the square root of 1 squared plus 4 squared, which is going to be a little bit of a nasty number. That's 1 plus 16, which is 17, so root 17. Now, we can put in our values here. X is 1, R is root 17. And at this point, the question doesn't ask for a decimal. You don't need to provide one, but you calculate it out as I have to 0.243 if we need to round. The question doesn't specify, so we can calculate the ratio. Probably to 3 decimal places is fine for most of these questions. Approximately equal to 0.243. Again, those that are trying to make some connections here, if I asked, okay, well, what is this angle? You now know the ratio. You were using the points to solve for it. Approximately 0.243. Angle A itself would be the inverse cosine of the ratio. All right, and we've done that before. So to tan now. Tan A of a point 6.3, which is also going to be in quadrant 1. So tan A for 0.63. Let's locate our point over 6, up 3. Draw your terminal arm. Drop down to the x-axis, which is always your initial arm. You rotate counterclockwise, if you haven't noticed that yet. I haven't mentioned it, but that's the direction we're rotating to form this angle in standard position. Label our side lengths, 6 and 3. This is a right triangle, has a terminal arm length r. Our point is at the end of the terminal arm. As always, we can calculate here, if we are dealing with tan, the ratio, which depends on the y and the x coordinate, meaning r is not needed. Hooray, finally we have to calculate anything with the Pythagorean theorem. It's just a straightforward calculation using the coordinate ratio, which is y over x, which would be 0.5. So a simple tangent ratio of 0.5. Again, if the question had asked, how do we solve for the angle? Again, for this one, knowing that it's a tangent, it'd be inverse tangent of 0.5 would be our angle. Okay, I'm going through lots of examples in this video because you really need to see how to solve different types of problems. But again, we're going to be going back to our coordinate definitions for the ratios, and we really need to reinforce that. So different types of problems approaching these ratios, maybe with different information. And then number 4, 5, 6, and I'm going through number 10. It's very predictable how we start. Use a relationship you know, and usually the math, the algebra is pretty simple. It's just setting it up. So first of all, take note of the important information. This is an obtuse angle, which means it's going to be located in quadrant 2. We're being asked to find the angle, given that it has a sine ratio of 0.23. So what does that mean? Okay, well, it doesn't mean the angle is 0.23. It means the sine ratio. So the sine of this angle. So let's write a relationship here. P is the angle. It has a sine of 0.23. All right, now remember, the sine ratio has two possible angles that have the same value. And that's because when we look at our coordinate definitions, sine is y divided by r. And the y coordinate can be the same in quadrant 1 and quadrant 2 because they're both positive. So going back to our example, there's two methods shown in the textbook the way we can approach this problem. We can either say that the sine of p is equal to sine of its supplement. We know that's true, where p and s are supplements. And if we do that, then we can solve for the supplementary angle directly using the fact that sine of the supplement is also equal to 0.23. And in that case, we can calculate the supplementary angle. But what you're going to find is when you take that equation and go to solve for the angle, and you use inverse sine of the ratio, here's what you'll get. Well, you're going to get 13.3 degrees. Now what you need to prepare yourself for is that the calculator doesn't understand the problem. What it does understand is that a sine ratio of 0.23 has an acute angle of 13.3 degrees. Now in this case, it worked out for us because we knew that P was obtuse. Okay, had we tried to solve this problem by assuming that, well, P is obtuse, so if I take the inverse sine of 0.23, I'm going to get my obtuse angle. We'll be fairly disappointed. And what you should take note of in the textbook describes this as well on page 22 in the margin, that your calculator will always return an acute angle when you evaluate the inverse operation. So what we're going to have to now look at here is that, okay, well, the relationship between angle P and angle S is their supplements. So one is the other subtracted from 180. And if we subtract 13.3 from 180, we'll get our answer. Okay, now approximately equal to here in this question to the nearest degree, we can go with 167 degrees. Okay, number 5, part A. Try and understand cosine ratio here. Now, cosine ratio, adjacent divided by hypotenuse, always worked pretty straightforward. Now, we get a cosine ratio of negative 0.67. Okay, a little bit of a red flag should go up here before. That's never happened where we have had an adjacent divided by hypotenuse ratio giving a negative value. For one thing, in a right triangle, an acute right triangle, where the angles are all less than 90 degrees, we can't have a negative length. Okay? With our coordinate definition, we can move outside of quadrant 1 and quadrant 2 locations, the points in that quadrant can have negative x values. So we should be thinking right off that because the ratio is negative, the angle must be in quadrant 2. Okay? If you don't recognize that, well, just see how the math will play out. If we attempt to solve for the angle given a ratio, and as we reviewed before in section 1.1, when you know the ratio and you want to solve for the angle, you evaluate the inverse operation, in this case cosine of the ratio, and that will give us the angle. Try that on your calculator. Inverse cosine 0.67, we get 47.9 degrees. Ha! I made a mistake, and you probably caught it. It wasn't 0.67, it was negative 0.67. Now, if you hadn't caught that, and you got an answer of 47.9 degrees, you might have thought, it's all good, move on. But had you made this initial observation or prediction, that should have stood out as a big error, because 47.9 degrees is not in quadrant 2. Let's try this calculation again. Inverse cosine of negative 0.67 gives us 132.1 degrees, but rounding to the nearest degree, 132. Fortunately, no special adjustment is needed. This is an obtuse angle. It is in quadrant 2. It fits with the question. The supplement of 132 degrees would be in quadrant 1 and would not have a cosine ratio of negative 0.67, because we have to remember that an angle and its supplement will have, for cosine, opposite ratios. So we're just using straightforward trigonometry, inverse operations to solve for the ratio here, and the only thing that we've been able to add to the solution is that we now can predict where the angle should be. Number 6, chose part B here. Wanted to use a negative tangent ratio. Okay, so a tangent ratio of negative 1.6 degrees translates, using the word of, is replacing equals. Tangent is negative 1.6 degrees. That would be another way of expressing that. So a tangent ratio is negative 1.6 degrees equal to, all right, now let's approach this as we've done before. The math, again, is usually not the difficult part. The calculator work is straightforward. Inverse operation applied to solve for an angle from a ratio. And let's just, before we calculate this, make a prediction. Where is the tangent ratio going to be negative? Less than 0. Well, we know that tan is, for an angle, equal to the ratio of y over x. So in quadrant 1, is x negative? No. In quadrant 2, can x be negative? Yes, it can. What about y? Quadrant 1, y is positive. In quadrant 2, y is positive. So the only thing that's making this tangent ratio negative is we must be in quadrant 2, where x would in fact be negative. Okay, a positive number divided by a negative number will give you a negative number. We don't really know the coordinates of this point, and that's another thing to take note of, is we don't know what two numbers divide to give negative 1.6, but we really don't need to, because once we have the decimal form of that ratio, we can just use it, and inverse operation will give us the angle. Okay, but a little prediction, this must be a quadrant 2 angle. Okay, let's take our calculator to task here. Second function tan, negative 1.6, and I get negative 58 degrees. That's what the calculator gave, negative 58 degrees. Now this is a little bit troubling because we haven't introduced or defined what a negative angle is. Positive angle rotates counterclockwise from the initial arm, which means that negative angles rotate counterclockwise, which means that quadrant 4 is actually the location of our angle. However, we're working for obtuse angles in this course between 0 and 180. So let's try to understand where this angle is actually located in quadrant 2. Well, probably the best way for me to reconcile this is for you to appreciate that an angle in quadrant 2 with the same slope would be easy to find if we just extend that negative 58 degree angle back along a straight line. And in that case, if this is 58 degrees down in here, then this will be 58 degrees right here. Okay, because we have opposite angles. This angle and this angle are opposite. Okay, so what is our actual answer? Well, it would really be the supplement to 58 degrees. Okay, it would be the supplement to 58 degrees. Okay, before I have students starting to snap their pencils and sign up for withdrawal lists at the guidance department, let's just reevaluate this question, and without having to introduce new ideas for negative angles and without having to go outside of quadrants 1 and 2. How could we have solved this problem? Okay, let's go back to what we had discovered earlier with the relationship between the ratio for an angle and its supplement. Okay, this is why we take notes. Your notes are a valuable resource. So if you're watching these videos and you're not filling in your notes, you're not doing your job as a student. The expectation is you're recording the information because you're going to go back and use it. You're going to study from it for tests, you're going to use it for the exam, and you're going to use it throughout the chapter. So we're going to go back and use this as a reference. When we're looking at trigonometric ratios of supplementary angles, it was understood that the sine ratios are equal, the cosine ratios are opposite values, and the tangent ratios are opposite values. The reasons were given, it was explained already. So what we want to do is go back to this relationship for tangent ratios of supplementary angles are opposite values. Let's use that. Okay, so if Q and S are supplements, let's get rid of this over here and simplify our solution. Q and S are supplements or supplementary, and because of that we can state that the tangent of Q is equal to the opposite of the tangent of angle S. So if it's the opposite, then we would be able to say that the tangent of the supplement would be positive 1.6. If the tangent of Q is negative 1.6, then the tangent of the supplement must be positive 1.6. Let's see if this helps. Okay. Now, if I introduced those relations before, we never actually used them, it would have been useless information. So now we're finding a reason for the relationships that were shown before. Okay, so here we're not going to directly be able to solve for the angle Q unless we understand what negative angles mean. Now, having not known what we were going to get when we evaluated the inverse tangent of a negative value, we couldn't have necessarily ruled that out as a good strategy. It seemed to work for us okay here because for cosine, the inverse cosine of a negative value in this case give us an obtuse angle which fit the situation. Here, inverse tangent of a negative value gives us a negative angle. Okay, you'll have to just work with the way the calculator is programmed in this particular case. solving for the supplementary angle first, I think, is going to be the better approach. So the inverse tangent of positive 1.6 is going to give us the supplementary angle, which is 58 degrees. And of course, we know that supplementary angles add up to 180 degrees. So what adds up to 180 degrees when 58 is one of the numbers? Well, it would be 122. So angle Q is equal to 180 degrees subtract angle S, which would be 122 degrees. And as I had shown before, we really were looking at a situation where 58 degrees off a straight line in quadrant 2 must mean that we were 122 degrees from our initial arm, and so our visual here would be of an angle that's 58 degrees here and 122 degrees here, which would represent our quadrant 2 angle as we predicted. Okay, so let's look at this problem here. We have three ratios, three different values, and now we're looking for all the possible angles that could occur in a triangle. Now this starts to hit home a little bit more because when we're working with triangles, and let's say we're solving a triangle using maybe the Pythagorean theorem, maybe the sine law, maybe the cosine law, sometimes we find that we go to perform a calculation and we get an answer, but it doesn't quite fit the diagram. And you may find that because trig ratios are now using coordinate definitions, there may be two different points that have the same trig ratio. And when you go to find an angle from a ratio, you may find an angle that fits a different triangle but would have the same ratio. Now, for quadrants 1 and 2, that only happens for sine. And you can remember that and take note of that. So for this question, really it's only A that's going to give two possible angles. Because in a triangle, you can't have an angle any more than 180 degrees. So we're really limited to angles in the first and second quadrant. Okay, now let's just use that to our advantage. In this case, for tangent, it's positive. And the tangent ratio is y over x. So how could we get a positive value for a ratio? Well, either y is positive and x is positive, two positive numbers could give 0.21, or y is negative and x is negative. Now where would a positive positive or a negative negative point be located? Let's have a look. Okay, in this diagram here, sort of shows the whole 360 degrees that might be possible for angles. And although we're only studying trigonometric ratios for acute angles and obtuse angles in quadrant 2, we could at least make connections here with other quadrants. And the negative negative quadrant, you'll notice, because tangent represents slope, look at all these lines. They all have positive slopes, don't they? And the reason for that is because in quadrant 3, the x and the y coordinates are both negative. And so a ratio of two negative values will give a positive tangent ratio. Okay, now that's not possible in a triangle. It could not have an angle in a triangle between 210 degrees and or between 180 rather and 270. It's not possible. Okay, so that's not an option. For us, the only option would be the positive positive quadrant. So for a tangent ratio of 0.23, or 2:1 rather, we would have to be in somewhere within quadrant 1. Okay, let's go back and solve for what that value would be. Okay, so I think it's important that when you go to solve a question like this, you make a simple statement. I've just reasoned out, based on how numbers work, that when a ratio is positive, and that's what that is, it's a ratio. How do you get a ratio to be positive? Well, either both the top and the bottom have to be positive, or the top and the bottom have to be negative. Okay, that's something that we should have understood about numbers and fractions before. So now we see how it's applicable here. We're talking about in which quadrant would you have two positive coordinates or two negative coordinates. Well, only in quadrant 1. So only for an acute angle could you have that. And of course, it has to be in a triangle. So we could only have an acute angle possible, and that would be 11.9 degrees. Let's look at moving backwards, B. Okay, so because the cos ratio is the ratio of x divided by r, and by the way, r is never negative. The length of the terminal arm is always a positive value. So these coordinate definitions, the only possible values that can be negative are the x and the y. Okay, and that's how the system works. So really when we're looking at these ratios that involve r, think of r as being a positive value because the square root of x squared plus y squared is going to be a positive value. And in this case, if it's negative, obviously the only option is the top number must be negative, because a negative divided by a positive will give a negative ratio. This is the only place where we can get a negative cosine ratio would be in quadrant 2. Now again, if we want to solve for this angle, just use our inverse cosine of negative 0.85, and we're going to get (148 degrees). All right, group. This marathon video continues. At this point, we're almost done. I just have one more example I want to go through, and you should have done a little bit of practice at this point, probably in class. And so you're coming back to this for additional examples, or if you want to review the examples that were already shown, because you just haven't got it yet. Have patience and just take the time to go through this. This will be the hardest part of chapter 1. When you get to sine law and cosine law, which you've seen before, it'll be a breeze compared to this. So don't think that it's just going to get harder from this point on. This is a very challenging topic. All right, we had done B and C. They've been cleared out now. Let's look at A. Again, using that similar approach, let's just write down what we know. We know the sine ratio is equal to, by coordinates, the y value divided by the length of the terminal arm. This is a positive number. So how can we get a positive ratio? Well, as mentioned before, the terminal arm has, by definition, a positive length. The x and the y coordinate, because they're on axes, can be positive or negative. Now, to get a positive ratio, we would have to have a positive y value. Of course, positive y is possible in quadrants 1 and 2. Okay, so this is not a new idea. We've seen this before. We know that the sine of an angle is equal to the sine of its supplement, which means because they're equal and not opposite, there are two angles. An angle and its supplement will have the same sine ratio. So we're dealing with angle G here. So we can really look for the value of G first, and then we can solve for its supplement. Or we could state right off that the supplement is also equal to 0.62. Well, now, of course, in this case, if we go to solve for the angle, it doesn't matter which angle we use, the operation is going to be the same. Inverse sine of 0.62. Calculator, of course, is only going to give one answer for this. Calculator doesn't understand the problem you're trying to solve for. Calculator is designed to give program response for a particular operation, and the inverse sine of 0.62, the calculator has only one way of getting an answer for that, and the answer it spits out is, of course, the acute or quadrant 1 angle. So where's the second one? Well, we remember that angle G plus angle S by definition, supplements add to 180. So that means that the supplement is 180 degrees subtract the acute angle, and that would be 180 subtract 38.3, which is going to be 141.7 degrees. So now, possible in a triangle. Can we have a 38.3 degree angle in a triangle? Yes. Can we have a 141.7 degree angle in a triangle? Yes. It might look like this. Here's your 38 degree angle. There's a triangle. Let's draw 140. 1.7 degree angle. There it is. There's a triangle. All right, last problem, number 13. Cosine of an obtuse. Last question group, we made it. Last example for part 2. Cosine of an obtuse angle is negative 0.45, and here we're crossing over from cosine to sine. Okay, so what we want to start with is the information which we know. We don't know the angle, let's just call it angle A. Cos of A is negative 0.45. Okay, now take note it's an obtuse angle. So an obtuse angle means it's in quadrant 2 as far as we're concerned. That would be the only location that we know of where an angle could have a cosine of negative 0.45. There is another location, but not between 0 and 180 degrees. So we can approach this a couple ways. We can either say that the cos of A is the opposite of the cos of its supplement, which is negative 0.45. This is still equal. Okay. We could then say that the cos of the supplement, well, I don't want to say two negatives make it positive, but it works here. If the opposite of negative 0.45 is got to now be the cos of the supplement, then that would be positive 0.45. Except, of course, here we're not looking for the supplement, but we could find the supplement and then go back and solve for the angle. That might be one way to go at it. Now, we saw before, though, if we took the inverse cosine of a negative number, we did actually get an obtuse angle. So let's use experience here and say that inverse cosine of negative 0.45, 116.7 degrees. And in this case, that is quadrant 2, obtuse angle. So that's confirmed. Calculate the sine of this angle. Well, sine of the angle, that's really easy. Sine of angle A is sine of 116.7 degrees. Now, 116.7 degrees is in quadrant 2, but we know that sine is positive in quadrant 2. It's also positive in quadrant 1. Doesn't really affect the math of this. We're just going to take the sine of that answer, which is 0.893. So sine of that angle A is 0.893. Just an interesting little twist on this, just to close out though, is this: if you actually take the inverse sine of 0.893, guess what? Your calculator is not going to give you 116.7 degrees. It's going to give you the quadrant 1 acute angle, and that's just the way the calculator is programmed. Okay, so if you take the inverse sine of 0.893 as a ratio, you're going to get 63.3 degrees. Is that a problem? No, because 63.3 and 116.7 are actually supplements. So what I would point out here is that the acute angle in quadrant 1 is supplementary to the obtuse angle in quadrant 2, and they both have a sine of 116.7 degrees. Congratulations, you made it through. Might even be the toughest lesson of the year. No joke. Check for understanding. Those questions probably already been done in class. Testing your skills with the remainder assigned there, 7, 8, parts of 10 and 11. And I'm looking to be collecting from you sometime within the next part of this week, number 12 and 14. And I want to see a diagram for number 14, including the point on a grid as I'd modeled to you before. Okay, well done for making it through. See you in class tomorrow.